Hi again. Welcome to the first of the videos on mathematical induction. This video explains the nature of deductive proof in mathematics and demonstrates the technique of induction with 3 examples based on different types of series. Mathematical induction is a method used in formal proofs. It is an example of deductive reasoning. A formal proof is a finite sequence of statements, and each statement is what we call an axiom, which is an assumption or a proposition which is assumed so that we can study its implications and consequences. We then make deductions from the sequence statements we prepare to reach a conclusion about which we have a logical certainty. In mathematical induction, we proceed with the following logic. First, a statement is known or assumed to be true for a given natural number, say for k. Second, we need to prove that statement is also true for the next number, which would be k plus 1. If successful, we try to then prove that the statement is true for an appropriate smaller natural number, and often the number 1 is used for the smaller number. On the basis of these proofs, we can then deduce that if it's true for k and for k plus 1, and then the statement is proved true for k equals 1, then it must be true for the next number, which is k plus 1, i.e. for 2. If it's true for 2, it must be true for the next number as well, that's for 3, and so on and so forth. So these are the strategies and conditions for mathematical induction. They are always inferred by using that term. When we're doing induction, there's always an initial statement, which we call the induction hypothesis, and this is often designated with SN. It is that statement that we have to prove. The statement is qualified also by providing a natural number, that is, a positive integer, which will be the lowest value for which the statement might be true. The steps we then follow, as described previously, are referred to as the induction steps. They are always the same, and they must be followed explicitly every time you do an induction. From our perspective in the senior high school, 2 of the common types of questions using mathematical induction focus on, first, series questions, which are terms being added together, and they're rarely of the common arithmetic or geometric types. And secondly, divisibility questions, determining whether an expression can be divided by a given natural number or by another expression. In this video, we're restricting ourselves to series questions, not to divisibility questions, so we'll start with a basic type of series question. We have to prove that 1 plus 4 plus 9 plus n is equal to n times n plus 1 times 2n plus 1 all over 6, and we're restricted to the n being greater than or equal to 1. So step 1, we have to prove the initial statement true for n equals 1. So looking at the left-hand side, our last term is n, so we just substitute 1 into that, so left-hand side is equal to 1. And for the right-hand side, we substitute 1 into that, which gives us a 1, times 2 times 3 all over 6 equals 1, so therefore it's true for n equals 1, and we write that. Going back to the steps that we talked about earlier in this video, we're going to now do step 2. We're going to assume that the statement is true for n equals k. So if that's the case, we can write 1 plus 4 plus 9 plus k is equal to, and we're just replacing the n with the k. So it's k plus 1, 2k plus 1 all over 6. Now the next step is to prove the statement true for the next value of k, which is k plus 1. So what we're doing is RTP, which is shorthand for required to prove. So we're required to prove the following relationship, that 1 plus 4 plus 9 plus up to k, and then we add a next term, which is k plus 1, is equal to, now we replace the k's in the term with k k plus 1, and so it's k plus 1 times k plus 2 plus 2k plus 3 all over 6. So now we have to prove that. So left-hand side is equal to, because that's the traditional way of doing it properly, we rewrite the expression for 1 plus up to k with the thing that we've assumed in step 2, which is k plus 1, 2k plus 1 over 6, and then we add our k plus 1. Now we have a common factor there of k plus 1, so we'll take that out, and we're left with k times 2k plus 1, which is 2k squared plus k, and then bring the other bit to a common denominator, so it's 6k plus 6, and it's all over 6. Tidy up, we have k plus 1 times 2k squared plus 7k plus 6 over 6. Factorise, we have k plus 1, 2k plus 3, k plus 2 all over 6, which is of course the right hand side. Now we don't go through all the rigmarole of saying if k is equal to 1 and so on and so forth. We simply write the statement that it's proved true by mathematical induction for n greater than or equal to 1. Don't, for heaven's sake, try to remember all that other thing. The examiner's not interested. They know what mathematical induction implies, so they will give you the full marks just for writing the statement I've got there. The second sort of series question is going to be involving fractions. So we might have, for example, that Sn is equal to 1 over 1 times 4 plus 1 over 4 times 7 up to 1 over 3n minus 2 times 3n plus 1, and that's equal to n over 3n plus 1. The restriction is that n is greater than or equal to 1. So we have to prove the initial statement true for n equals 1. So the left-hand side, we just substitute into our last term, which is not a bad idea, rather than just use the first term. Should be the same. 1 over 3 times 1 minus 2 is 1, times 3 times 1 plus 1, which is 4. So 1 times 4 is a quarter, so that's good. The right-hand side is 1 over 3 times 1 plus 1, which is a quarter, so good. It's true for n equals 1. So now, same deal, step 2. We're going to assume the statement is true for n equals k. So we rewrite the first few terms, 1 over 1 times 4, etc., just to get us moving. And then we're substituting k for the n terms, so 1 over 3k minus 2 times 3k plus 1 equals k over 3k plus 1. Now step 3 is to prove the statement is true for the next number, which is for n equals k plus 1. What we're required to prove is exactly what we'd written down on the left-hand side in step 2, plus the next term for using k plus 1, so it's 1 over 3k plus 1 times 3k plus 4. It came from 3k plus 3 plus 1, and that's equal to k plus 1 over 3k plus 4. Now to prove that, left-hand side equals, we write it down and replace all of the first terms with what we've assumed in step 2. So k over 3k plus 1. Add the last term, which is the k plus 1th term. We've got a 3k plus 1 in the denominator, so factorise that one out, and sort of we're left with a k plus 1 over 3k plus 4. So we'll bring that to a common denominator of 3k plus 4. So multiply through, we've got k times 3k plus 4 is 3k squared plus 4k plus 1. And then we can factorise that. So we've got 1 over 3k plus 1 times 3k plus 1 times k plus 1 all over the other denominator, 3k plus 4. The 3k plus 1's cancel. We're left with k plus 1 over 3k plus 4, which is the right-hand side that we assumed. So we've proved by mathematical induction for n greater than or equal to 1. Don't write more. Now there are a few ways that the examiners can ask you questions about induction related to series, and some of those are dealt with in the website, but the one I want to deal with here is going to be with the factorial notation. For example, we might have to prove that 2 times 1 factorial plus 5 times 2 factorial plus 10 times 3 factorial plus n squared plus 1 all times n factorial is equal to n times n plus 1 factorial. So we've got to know our factorial notation in order to do these questions. Step 1, prove the initial statement true, as usual, for n equals 1. The left-hand side is equal to 1 squared plus 1, which is 2, times 1 factorial, which is 1, so it's 2. Right-hand side is 1 times 2 factorial, which is 2, so therefore it's true for n equals 1. Moving on to step 2, we have to assume that the statement is true for n equals k. So it's 2 times 1 factorial up to k squared plus 1 times k factorial is equal to k times k plus 1 factorial. So we've just replaced the ends with a k. Normal procedure. Step 3, we've got to prove the statement is true for n equals k plus 1. So here we've got to change our k's to k plus 1. In the required to prove statement, we've got all the same ones as we had in step 2, plus the additional term, which is now, be careful, the k is replaced with a k plus 1. So we've got k plus 1 all squared plus the 1 times the k plus 1 factorial, be really careful with that one, equals k plus 1 times, now the brackets is k plus 1, which is k plus 2 factorial. Left-hand side equals k times k plus 1 factorial, which is just taking the statement assumed in step 2, plus our k plus 1 squared, etc. Now we've got a k plus 1 factorial in both of those terms, so we can take that out, and we're left with a k plus 1 squared plus 1, which is going to give a k squared plus 2k plus 1 from the second term, plus another k from the first term, which is a k squared plus 3k plus 2. Factorise that, got a k plus 1 factorial out the front, then a k plus 1, k plus 2. The k plus 2 merges in with the k plus 1 factorial to give us a k plus 2 factorial. So that's the term we've got, and that's of course equal to the right hand side. So we now conclude in our straightforward statement, proved by mathematical induction for n is greater than or equal to 1. So that summarises the concept on proof by mathematical induction, as well as showing you the strategy to use for questions involving series. In the next video we will demonstrate the induction technique on questions related to divisibility. Consolidate what you have learnt here by doing the induction series Test Yourself 1 questions on the website drjaysmaths.com. Hit the like button and subscribe if you haven't already, then you get notifications about new videos. Good luck. See you in the next induction application video. Bye.